Hi, everybody. My name is Kuassi Mensah. With me, Paul Parkinson. You cannot see Paul, but he's behind me. And so we will be presenting you the microservices, data challenges, and solution with Helidon and the Oracle database. So let me share my screen. Here we go. So I do product management for anything Java connecting to the Oracle database. Paul is dev transaction processing dev lead in the microservices cloud platform. Here is the agenda. I will discuss the challenge of persisting events and state. I will also discuss the issue with high concurrency, what are the locking techniques and the impact in terms of data consistency. Then Paul will take a significant amount of time to explain to you all the issues and the solutions around distributed transaction across microservices. Then he will also show you a nice demo which captures all those concepts and put those in perspective. So why is persisting events and state a challenge? So first, let's look at microservice communication. Microservice communication could be synchronous using REST or gRPC or some other synchronous communication protocol. Or it could be asynchronous, and this is more what the market, the community at large has been using. You could combine both, you can have front-end receiving REST calls, and you can have communication among the other services using asynchronous communication. Anyway, the issue at hand is I'm doing asynchronous communication. This is low scoping. The events are immutable. You cannot change them once you emit them. It's message-based, it's pub sub, etc., etc. There is a notification, there is a broker, and it's commonly known as event sourcing. So let's look at what event sourcing is. Event sourcing means, for those not familiar, microservices interact by sourcing event in and out from the event store, and they get notified by the service broker. So in this example, in this picture, order service will receive an order from the front end, will make changes to data, will persist the event into the event store. That broker, the event broker, will notify interested party. The inventory service is an interested party registered to receive notification from the order service, will be notified that there is an event produced by the order service, but it will get the event from the store. The event store is the source of truth. Right. Okay. So what is the problem? Well, the problem is I need to persist my changes to the database, and I also need to persist my changes to the event store. And I want both things to be one single atomic local transaction. It's not two-phase coming here. Right, so that's the challenge. What are the solutions? You could use something known as outbox table. I discuss more in the next slide, but in a summary, in one sentence summary, you have a process which will tail the transaction log, and whenever there is a new transaction, you're gonna publish an event to the event store. Okay, so we look at this in the next one. And then there is this database table as a message queue, which is a manual invention of what I will describe later, which is the advanced queuing. The problem with this second approach that I will not elaborate, but just talk right now, is that what about the scalability, and what about cross microservices, cross database exchange? How are you gonna do that with a table per database or per microservice? How do you deal with that? So it's a manual, but it's not easy to to get right. And then there is the advanced queue solution. Outbox solution, this is it. So you get a connection, you make data changes, you make an insert, an update, and delete to the table, to your schema, multiple tables, presumably. And then you have a pseudo table called the outbox table, where you will insert a pseudo event. So once you've done, you commit, so it's a local commit, but subsequent step, you need a process which will tail the transaction log and then will publish an event from the transaction log to the event store. So the event store is a separate entity and it's like a two-steps operation. So this is a little bit complex and it has some impact in terms of scalability and mining the transaction log, etc., etc. Anyway, people can use it, it works. The AQ approach, pardon me, the AQ approach is like this. The same connection, the same database connection will be used for data operation on the tables and also AQ or queue or event operation because AQ is built into the database, okay? But it's not just built into the database as a table. No, it's an event system. It is an event broker, and it can propagate events from one database to the other, assuming the other database also have AQ in it. So it is a complete event mechanism, but it's distributed and reside into the Oracle database. So from the NAQ session, we can get a JDBC connection and do all the database operations. I mean, all the traditional DML, and then do the queue operation as well. And then we commit. When we commit, well, AQ, we publish the event. So this is simple and it scales well and it is distributed, okay? And we will talk, Paul will talk about it as one of the approach in his demo or in his distributed transaction, and you will see how it plays nicely. The second challenge I want to talk about is the high concurrency. What are the impact in terms of locking and data consistency? So 3 locking mechanisms that people use, I mean, that it's known in technologies, okay? So what is the impact on shared data and data consistency? So 3 techniques: pessimistic locking, optimistic locking, and escrow locking. Here we're talking about concurrent access to the same item. For example, I want to purchase the t-shirt by Paul Parkinson. So I need everybody's asking for that t-shirt. So it's in terms of inventory, it's one item. It has multiple quantities, but it's one item. Okay, so pessimistic locking means as soon as one person or one process or one microservice issue a request to update, I'm gonna place a lock. So I'm gonna place a non-shareable lock, an exclusive lock. This forces everybody else or every other processes or microservices to be serialized behind me. It's only when I'm done that they can access the inventory. So it has limited concurrency or scalability, which is not so good for microservices, but it has the benefit of the ACID properties, the database ACID properties, so there is no dirty read. Then we have the optimistic locking. So the optimistic locking, the main characteristics are shared locks. So multiple transactions can access the same item at the same time or quasi same time. It depends when they come. And then the actual update is only performed at commit time, at transaction commit time. The actual update to the database, to the inventory. So let's look at this. So transaction 1 issue a request to purchase 5 items. We have 10 in database, 10 minus 5 is okay, but we are not making the change right now. We're not making the update now. So transaction 2 comes in and say, I want to purchase 3 items, the same item, and this could be going on concurrently because they are shared logs. So we look at the inventory, we have 10 minus 3, that's okay. Transaction 2 make a commit. So this is where the actual update will happen. And you can see that in the database, in inventory, we now have 7 items. Transaction 3 comes, make a request to purchase 5 items. 7 minus 5, it is okay. Transaction 3 commits. Now we have 2 in inventory. When transaction 1 commits, well, it's too late. We only have 2 in inventory. So no, can't do it, roll back. So what is the drawback of this? Well, you could have dirty reads, and insufficient inventory at commit time will force the older transaction to roll back. The benefit is this concurrency, high concurrency, parallel update on shared data, which is what our goal is, to have parallel update on shared data. Okay, so could say mission accomplished. Okay, and the third locking mechanism is known as escrow locking. People who bought real estate in the US know what escrow means. Anyway, the mechanism here are shared logs, but we use the journal to allow or reject based on what is in the journal. So we make promises, and based on the value we have in the journal, not in the database. And same here, the actual update is performed at the transaction coming time. Now, if we look at the animation here, transaction 1 make a request to purchase 5 items. In the journal, we have 10. This is the beginning, so it's the same value as in the database. So 10 minus 5, yes, we can promise transaction 1, you'll get 5 items. So now in the journal, we only have 5 items, even though in the database there are 10. Transaction 2 comes and makes a request to purchase 3 items. We look at the journal, 5 minus 3, that's good. So we promise transaction 2, you're gonna get 2 items as you wish. Transaction 2 commits, and this is where we make the actual update to the database. So it goes from 10 to 7, but in the journal, we still have only 2 based on all the promises we have made so far. So transaction 3 comes and issue a request to purchase 5. We said, nope, looking at the journal, not enough, even though there are more in the database. So we force transaction 3 to roll back. When transaction 1, who were promised 5, comes in, he gets its 5 items. And now in database, we have 2 in inventory. So the benefit here is high concurrency, parallel update. We could use the journal to implement the compensation if we were in the situation where we have distributed transaction using the saga pattern, but Paul will talk about it, but the journal is a very important mechanism in that situation. Okay, so the difference between escrow locking and the optimistic locking is that in here, the younger transaction will be forced to roll back, whereas in the other case, it's the older transaction. And here we can also use the journal to do compensation in case we are having distributed transaction. Okay, so that's all I have, my part of the presentation. Paul will now talk to you about distributed transaction, all the challenges and the solution that we provide. Okay, so I'll see you on the Q&A.
Thank you, Kuassi. Distributed transactions across microservices. So on the left side, we have a diagram from the XA specification, and on the right side, we have a snippet from the saga specification. So the XA specification and two-phase commit are distributed locking consensus protocols that are, have been used for decades in enterprise systems. And although they're not specifically saying this in the specification, notice that the application program is in a single block on the left there. And as well as the transaction manager. And the application program is talking to multiple resource managers. That transaction is coordinated by the transaction manager. And most often, the application program is actually in the same process as the transaction manager. So now if you start to look at microservices, where the application program is not a single process anymore, it's not a monolith or whatever you want to call it, it's multiple services, and each of those services is talking to its own resource manager. What you've done is a number of things, but one of the biggest things that's happened is you've obviously introduced more network into the program, the overall program. And with this network and various other aspects, you can introduce this latency, and that is going to limit what you can do as far as taking advantages of a microservice cloud environment. It's going to limit your scaling and throughput and things like that, and may even result in such a slowdown that you'll start to get locks held in doubt type errors. And so while it's not prohibited to run such applications in the cloud, and such, the application server WebLogic has done this very successfully, you won't, as I say, be able to take advantage of some of the scaling and other aspects of microservices. So that's where you kind of draw the line as far as what you're choosing, the trade-off. So to deal with that situation, the saga pattern, which is from the 80s actually, is being used because it deals with local transactions only. So the transaction local between the microservice and its particular resource manager, and the locks only exist there in a local transaction, not in a distributed transaction. And so in this case, because you don't have the nice asset properties and clean rollback call directly on the resource managers, you need to come up with a compensating action for each of the actions you take. And so that compensating action is going to be a local transaction as well, of course. And I think this really kind of sums it up, just this little snippet here, that the desired case is that you continue these transactions successfully, but if something goes wrong, then you replay their corresponding compensating activities. And of course, that's much easier said than done, but that is the basics of the saga pattern. Real quickly, in case you're not familiar, I just wanted to go over the kind of microservices landscape. At the top, we have larger solutions, such as if you want to call them legacy systems, the application servers and things like that, things that have been coined as monoliths, things like that. You start to move down. Spring Boot is quite large, but you're starting to move more into a microservice area. And then a MicroProfile, which is a set of specifications geared towards writing microservices. And so if you're familiar with Java Enterprise, that's these type of specifications, but again, geared towards microservices, and then even smaller frameworks than that. And so what we're going to be talking about most today is the MicroProfile model for writing microservices. So long-running actions, or LRA, is a specification, MicroProfile specification, and it's used, if you're familiar, again, with JTA, much like the @transaction annotation. So the @LRA annotation is used for two things. One, for demarcating a transaction boundaries. So it's used to start the transaction. And then it's also used to indicate that a service wants to be a participant in this long-running action, in this saga. And so again, it's similar to the @transaction annotation. What's the big difference between that and LRA and sagas is the need to define a compensate and complete methods on our microservices, because we no longer have that direct rollback against the resource manager. Microservices need to define and write their compensate and complete activities in order to roll back any actions in the face of a failure. And as far as the complete case, in case there's any kind of cleanup or action that should occur afterwards. Just very quickly about the last three. Forget is when the coordinator, and we'll get into the architecture a little bit more in a sequence in a moment. @forget is a method that is called when the coordinator wants a participant to forget about an LRA, so it can release resources and things like that. @leave is in a way sort of the opposite direction. It's a participant saying it wants to leave the LRA activity. And @status is a method defined on the participant that the LRA coordinator may call for a number of reasons. For example, if it did not get a clear response back from a compensation call, it will call status to see what the status of that participant is. So this is just very quickly what that looks like in code. Again, we have the LRA annotation on a travel agency service up at the top method here. It says requires new, so if this method's called, it will start an LRA transaction. And then the flight and hotel services have this similar format on the bottom, where the reserve method is called and an annotation with LRA type mandatory, and therefore that method must be conducted within the context of an LRA transaction. And then finally, the compensate complete status methods that I just mentioned. So let me just go through a quick sequence of events of how this goes. So you have a request to a travel agency app. And we saw that, that book travel method is annotated with the LRA annotation. And therefore the underlying LRA library calls the LRA coordinator and says, start an LRA. Returns to the travel agency. The travel agency makes an application call to the hotel service to reserve the hotel. Just the way the LRA library and the initiator, the travel agency, called start on the LRA coordinator, this hotel service will call join, and the LRA coordinator will join this service to the LRA, and it will receive the information as far as what the complete method to call, the compensate method to call, etc. That will return, and then the application response to the travel agency. Same thing for any other services such as the flight service. The travel agency will then, based on the replies from the hotel and flight service, indicate whether the LRA was successful or not. And that's generally done implicitly. That will be sent to the LRA coordinator. The LRA coordinator will then issue the complete or compensate method as appropriate on each of the participants that had joined the LRA transaction. That command is then returned back to the travel agency, that returns the result to the customer. And so what you just saw was LRA using REST. And so that is what is currently defined in the LRA specification. Intentionally, other aspects are not defined yet. So these other features I'm mentioning are Helidon specific. So the Helidon LRA implementation writing has messaging support. We'll see that in the demo. Kafka, and any kind of messaging, but of course, if you're using AQ, you're getting the advantages that Kuassi mentioned. LRA with REST and the Oracle DB Saga features Kuassi mentioned. The fourth combination being, you know, messaging with those Saga features. And when you use those two together, the logic, there's even more logic that's done behind the scenes for you as far as propagating the Saga and things like that. So you can get optimizations and less and simpler coding. And then just various combinations that we have as far as what we're building with between LRA with Camunda and the Oracle Process Cloud Service, so business process workflow engines, and interop with other languages. So .NET, Python, JavaScript, et cetera, being participants in an LRA activity. So this really is no exaggeration and is actually a very conservative comparison of what a developer faces, you know, kind of without these features that we're mentioning. So the estimate that seems to come back from anyone you talk to, it's interesting, is 80% of the development effort in one of these systems that relies on compensating activities goes to that compensating activity logic and the testing and things like that around it. And it can definitely become a real nightmare. And so especially if you have to do dupe processing, keep journals for all your compensating activities, you know, make sure everything's in order and all of these various aspects. And so you know, as it's running off the page on the left here, that's, you know, no exaggeration. And it's no exaggeration that, you know, a lot of this is, can be simplified, remove all this error-prone, you know, lines and lines of code by using the features we've been describing. So that's what you see on the right. And so in this example showing Helidon LRA functionality, I have a application which involves an LRA that has two participants, an order service and an inventory service. And so if an order is placed and the inventory exists, then the LRA is successful and complete is called on all the services. If it is not successful, if there's not enough inventory, then we will have the compensate activity initiated by the LRA coordinator and the compensate methods called on the participants. So I'll be going back and forth between three areas. On the left here, you see the terminals for the different services, the front end, order, inventory, and coordinator. On the right, you see the actual front end for the app, and then I'll be popping over to show you source code as well. So let me demonstrate the app first. We will go ahead and add inventory. So we see we have an inventory count of 1 here, okay? And then these are the various combinations that we have. And we will start by using REST communication, and then I'll show you the messaging communication. So we have inventory count. Let's go ahead and place an order. And we will see the order was completed successfully because we did have enough inventory. And so let's look over at our terminals here. Hopefully you can see them. Front end is just showing, you know, what we're basically seeing over here. In the order service, we can see that the order service annotation resulted in the LRA client there, the library, calling start on the coordinator. And then we can see on the coordinator side that start was called, and that the order service itself was actually enlisted in the LRA. And we can see the endpoints that were added, given to the coordinator by the library and the order service, okay? We then go ahead and call the inventory service from the order service to see if the inventory exists. We see here that the inventory service received the call, and because it had the mandatory LRA annotation, it called join LRA on the coordinator so that it now joins this LRA. So we now have the order participant and the inventory participant. The inventory existed. Inventory exists is true. That was returned to the order service. And because of that, we see inventory success, and is compensate is false. In other words, complete should be called. That is, the client calls close or cancel, and that results in the close being successful. So it results in complete being called on the participants, and then cancel results in compensate. So in this case, we have close. That was received by our coordinator, and it went ahead and did a call to the order service and the inventory services complete methods. Okay, so we saw success there. So then if we go ahead and remove the inventory and do the same thing, we will see the expected failed because the inventory doesn't exist. And then that same flow, you know, it was started, and the order service was joined into the LRA. The inventory service was joined into the LRA. But this time, since there was a failure of the inventory didn't exist, we call cancel. And then the coordinator calls the compensate method on the order and inventory service. Okay, so let's go ahead and look at the source for that real quick. What we have is the order resource. And again, just as I showed you in the slides, we see this, you know, requires new that came in. And then as a result of the successful case, we had complete order called. And in the failed case, we had cancel called. And this is the call from the REST call from the order service to the inventory service. And then, you know, the inventory service received it, checked the inventory, returned accordingly, and then its cancel or complete inventory methods were called by the coordinator. So that's our REST case. Let's go ahead and try this with messaging. So let's do the success case first again. Let's add inventory. But this time we're using messaging, so let's go ahead and place that order. And so what we can see here is the same process, but we're using messaging. So we got the start LRA called on the coordinator by the order service when it was started. You can see that the start was called here. I'm sorry, the start was called here, and the join of the order service for messaging this time. And then when the order service called the inventory service, it called join on the coordinator. And so we have the inventory messaging resource, and then it was successful. So the order service called complete, and a message was sent from the LRA coordinator to the participants to complete the order, complete inventory. Okay, and then just the same idea, of course, for the compensate case. We use messaging again, place the order, and this time, you know, we will get back the fact that the inventory does not exist. And so the order service will call cancel, and likewise the LRA coordinator will call compensate on the two participants by using messaging. Okay, so let's look at the source code for this. So I have the, you know, order resource and inventory resource, and then there's order messaging resource and inventory messaging resource. So let's look at the order messaging resource. And what you will see here is that by calling that, a message is sent, and we have this incoming order method. So the same LRA annotation, but instead of having, you know, our REST endpoint here, we are using the MicroProfile messaging specification. So another MicroProfile specification. And so that order, we then send a message. There are a few different ways to do this. In this case, we're explicitly sending this message out. The inventory service will then pick that up because it is listening on this order channel. And then it will check for inventory. And depending on that inventory level, we'll send a response saying whether the inventory exists or not. So let me back up a little bit on this, on the messaging, and explain what's going on here, because there are a number of things. So as I mentioned, we're using the MicroProfile messaging specification. And if you're not familiar with that, like a number of other things in MicroProfile, you have these MicroProfile config properties. And in these properties, you can define connectors for the messaging specification to whatever systems, Kafka, AQ, whatever system you may be using. And then you define these channels. And these channel names, again, if you're familiar with MicroProfile, it's a standard of the type and a name and then a value for that type that's named this. And so that channel name is what we're seeing in these classes here. So that channel name is order. And so it's listening on you can define it any way you like. Here we have actually defined queues for each of these, but more realistically, you would probably use the same queue and a selector and things like that. But in any case, hopefully you get the concept of it. This is what is defined in config as far as your incoming channel, whatever you're listening to. And then likewise, as we're looking at the inventory service, you have your incoming and outgoing. And so this is a very powerful little method here. What we're seeing is the order service has placed a order placed message. That order placed message is picked up by the inventory service. The inventory service is interested in orders that are placed. So the inventory service picks up that message from the order queue or what have you, and it then checks the inventory, as I say, and sends that inventory exists or not to the inventory queue. That inventory queue is being listened by the order service, and that's how the order service knows if the inventory exists or not. So this shows the power of the messaging, MicroProfile messaging and LRA together. But what you also see in this method is the power of using those together with AQ, because we know this was a guaranteed message delivery, and it's a guaranteed message, both incoming and outgoing. But what is two other aspects that are very interesting is that from the AQ message, we are actually able to get the underlying JDBC connection for that AQ resource. So the AQ is part of the database, so it's the same resource manager. And as Kuassi was saying, you can therefore conduct messaging and database work in the same local transaction. So we actually have 3 actions going on in the same transaction here. We're receiving a message about an order, we're checking the inventory, and then we're putting the response as far as whether the inventory exists or not on this inventory queue, all in the same transaction. So this is all atomic. So very powerful feature, and you can see how short the method is here. So very powerful. Then from then on, it's basically the same as the REST case, as you might imagine. The order service listens to whether the LRA, the inventory exists or not, and then as a result of that, implicitly will tell the LRA coordinator to complete or compensate, to close or cancel. And then we have the incoming methods for both participants for that, which is also in messaging. They receive messages from the coordinator. And so again, when that happens, we can get the JDBC connection and do whatever work we need if we're using AQ in this case. And so hopefully you get some of the concepts of LRA and the power of using this Saga support with Helidon and the database. And we'd like to open it up to any questions. One thing we want to mention very quickly is that there's a workshop for data-centric microservices that's being held at J4K. But in case you could not make it, you can actually do it on your own. If you go to this URL, you will see the instructions to do so. And so you can do it at your own pace, and you know, you can watch the video along with it and things like that if you'd like. So we're definitely interested in any feedback you have whatsoever and any questions, and I really appreciate your time. Thank you.